Hello everyone, welcome to EnviroPioneers. Through this video, we are going to start a new topic in our remote sensing and GIS playlist, that is microwave remote sensing. Understanding of this topic is very important as microwave remote sensing plays a crucial role in the Earth observation as it allows us to gather the information about the Earth's surface independent of sunlight and weather condition. We will explore microwave remote sensing topic in three parts. Part 1 will introduce the basic concepts including the microwave region of the electromagnetic spectrum, active and the passive sensing, as well as the radar fundamentals. Part 2 will focus on the key aspects such as the radar image geometry, relief displacement, image foreshortening, layover, shadows, and speckle. And part 3 will cover the concept of the synthetic aperture radar and the applications of the microwave remote sensing in environmental and the earth system studies. So let us start the basic concepts of the microwave remote sensing in this video. Till now, the topics which we have covered in the remote sensing and GIS playlist that comes under passive remote sensing systems. In passive remote sensing, sensors record the electromagnetic energy that is reflected in the visible or NIR range or the energy which is emitted in the thermal infrared range. So in passive remote sensing, the source of energy is sun and the energy which is reflected or emitted from the terrain that is recorded by the sensor. But along with the passive remote sensing systems, there are also active remote sensing systems that are independent of the sun's electromagnetic energy or the thermal properties of the earth. So in the active remote sensing system, sensors they create their own electromagnetic energy that is transmitted from the sensor towards the terrain. This electromagnetic radiation interacts with the terrain producing a backscatter of energy, and this backscattered signal is recorded by the receiver. So this active remote sensing systems include radar, LIDAR, and sonar. Radar is radio detection and ranging, and this is based on the transmission of long wavelength microwaves through the atmosphere and then recording the amount of energy backscattered from the terrain. Next is LIDAR, that is light detection and ranging. This is based on the transmission of relatively short wavelength laser light and then recording the amount of light backscattered from the terrain. Next is sonar, that is sound, navigation, and ranging. This is based on the transmission of the sound waves through a water column and then recording the amount of energy backscattered from the bottom or from objects within the water column. In these active remote sensing systems, radar is most widely used for the Earth resource observations, LIDAR is useful for the topographic mapping, and the sonar is useful for the bathymetric mapping. Each of these active remote sensing systems they work on different principle. In the first one, radio waves are used, in the second, light is used, and in the third, sound is used. But if you note, one thing is common in all these systems, that is the sensor record the amount of energy backscattered from the terrain. So we can see this thing is common in all the active remote sensing systems. It means in active remote sensing system, the source of energy is on the platform itself, which generate a signal that is transmitted towards the terrain, and then the receiver on the platform it records the amount of the backscattered signal. So in any of the active remote sensing system, this is very important concept because when a signal is transmitted from the source towards the terrain, this signal, or we can say the electromagnetic radiation, can get scattered from the atmospheric components in its pathway, or when it strikes on the ground, it can get reflected in any of the direction. So there is difference between scattering and backscattering. Scattering is the reflection of the waves in any of the direction, while the backscattering is the reflection of the wave back to the direction from where it is coming. So, depending upon the surface on which this electromagnetic radiation or the signal is incident, the sensor may or may not receive the backscattered signal. Because if the surface is very smooth, there will be specular reflection, means this electromagnetic radiation will be reflected in opposite direction. So there will be no return, means the sensor will not receive any of the backscattered signal. But if there is intermediate roughness, there will be some amount of backscattering, so the sensor will receive moderate amount of return. But when the surface is very rough, there is diffuse scattering, means reflection in all the direction, so the sensor will receive a strong return of the backscattered signal. So, depending upon the objects on which this signal is incident, the backscattering can be of different type. It can be surface backscattering, it can be volume backscattering, or it can be double bounce backscattering or diffuse backscattering. We will learn about these in more detail in the part 3 of microwave remote sensing. First, let us understand the basics of the microwave remote sensing. So, this microwave remote sensing uses the electromagnetic radiation with a wavelength from 1 centimeter to 1 meter. So, the electromagnetic radiation falling in these wavelengths are referred as the microwaves. And because of their greater wavelength compared to the visible and infrared radiation, these microwaves exhibit the important property of penetrating the clouds, fog, or if there is any ash or powder coverages, for example, in case of the erupting volcano or a collapsed building. Microwave remote sensing systems can be classified into two groups, passive and active. So, the passive systems collect the radiation in these wavelength range that is naturally emitted from the terrain under observation. So, the sensor which is used in the passive system is microwave radiometer. While the active microwave sensors, they provide their own source of microwave radiation to illuminate the target. In passive microwave remote sensing, sensor detects the naturally emitted microwave energy within its field of view, and this emitted energy is related to the temperature and the moisture properties of the emitting object or surface. So, the passive sensor placed on the platform can receive the microwave energy emitted by the atmosphere, reflected from the surface, emitted from the surface, or transmitted from the subsurface. As the wavelength of the microwave radiation are long, the energy of these radiation is less in comparison to the electromagnetic radiation falling in the optical wavelength. Thus, the field of view must be large to detect enough energy to record as a signal. So, most of the passive microwave sensors are characterized by low spatial resolution, and this passive microwave remote sensing has its application in meteorology, hydrology, and oceanography. Meteorologists use passive microwaves to measure the atmospheric profiles and to determine the water and ozone content in the atmosphere. Hydrologists use passive microwaves to measure the soil moisture, and in oceanography, passive microwaves are used in mapping the sea ice, currents, and surface winds, as well as in detection of the pollutants such as the oil slicks. Now, coming to active microwave remote sensing, in this, the sensors can be classified into two types, imaging and non-imaging. We have already covered about imaging and non-imaging sensors in detail in lecture 5 of this playlist. Imaging sensors are those which can generate digital image of the field of view, while non-imaging sensor provide us data of the intensity of the energy reaching to it. And the most common form of imaging active microwave sensor is radar. This stands for radio detection and ranging, and it characterizes the function and operation of a radar sensor. So, in radio detection and ranging, sensor transmit the microwave or radio signal towards the target, and then it detects the backscattered portion of the signal. Now, the sensor placed on this platform can measure two information about the backscatter signal, its intensity, and second is the time delay. So, the strength or the intensity of the backscatter signal is measured to identify different objects on the terrain. So, it is used to discriminate between different targets. And the time delay between the transmitted and the reflected signal determines the distance to the target. Example of the non-imaging microwave sensors are the altimeters and scatterometers. So the radar altimeters, they transmit short microwave pulses and measure the time delay between the transmitted and the received signal to determine their distance from the sensor. And it is mainly used on the aircraft for the altitude determination and can be used on the aircraft and satellite for the topographic mapping and sea surface height estimation. Scatterometers are used to make precise quantitative measurements of the amount of energy backscattered from the targets, and the amount of energy backscattered is dependent on the surface properties and the angle at which these microwave energy strikes the target. And these measurements over the ocean surfaces can be used to estimate wind speeds based on the sea surface roughness. Here are some of the major developments in active microwave remote sensing. The first demonstration of the transmission of radio microwaves and reflection from various objects was achieved by Heinrich Hertz in 1886. Then rudimentary radar was developed, which was used for the ship detection. In the 1920s and 1930s, experimental ground based pulsed radar were developed for detecting the objects at a distance. First imaging radar was used during the World War II. After that, side looking airborne radar was developed for the military terrain. In the 1950s, advances in the side looking airborne radar and development of the higher resolution synthetic aperture radar were developed for the military purposes. And in the 1960s, these radars were declassified and began to be used for the civilian mapping applications. In active microwave remote sensing, mainly side looking airborne radar is used. This is little different from the data acquisition method used in the optical and thermal remote sensing. Normally, a sensor placed on any platform covers an area just beneath it, and the area covered depends on the instantaneous field of view and the height of the platform above the ground level. And the data acquisition for the area is done either by the capture method, along track scanning, or across track scanning. But in the side looking airborne radar, the sensor looks at one side of the platform, means it is not acquiring the data exactly from below but from one side of its flying direction. In this image, we have two terms, nadir and swath. Nadir is the point on the ground directly below the sensor, as we can see in this case also. Swath is the width of the area on the surface of the earth which is imaged by the sensor during a single pass. So we can see in normal acquisition mode, nadir is the center point of the swath. But in the side looking airborne radar, the data is acquired from either left or right side of the nadir. Inside looking airborne radar, this signal is transmitted or received via antenna. So, based on the type of antenna used in this system, side looking airborne radar can be of two types, real aperture radar or synthetic aperture radar. So, this real aperture radar is also known as the brute force radar, and it uses an antenna of fixed length. It can be from 1 to 2 meter, and synthetic aperture radar also uses a 1 to 2 meter antenna, but here the system is able to synthesize a much larger antenna electronically. Means it can be of approximately 600 meter in length. So this synthetic aperture radar, it gives very fine resolution from great distance. For example, 11-meter synthetic aperture radar antenna on orbital platform. It can be synthesized electronically to have a synthetic length of 15 kilometer. Means यहाँ पे actual size is only 11 meter but the synthetic size is 15 kilometer. Active microwave imagery is obtained using the instrument and principles that are different from those used when acquiring the data in the optical or thermal infrared portion of the electromagnetic spectrum using the passive remote sensing technique. Therefore, it is necessary to understand the active microwave system components. Active microwave system, it can be mounted on the aircraft or it can be placed on a satellite, and this system consists of a pulse generating device. Here we can see pulse generator, then we have a transmitter, and then duplexer. So this duplexer is used to send and receive the signal. So it coordinate the transmission and receiving of the signal. Then we have an antenna where we have a receiver, a recording device such as the high density digital tape or the hard disk, and in the system mounted on the aircraft, a CRT monitor is also included so that the technician can check whether the data is being collected or not. So, this pulse generator generates a pulse of electromagnetic radiation which is transmitted through transmitter and this duplexer to antenna, and from this antenna it is transmitted towards the terrain. This antenna also receives the backscattered signal, and when this duplexer is in receiving mode, the backscattered signal is directed towards the receiver from where it is stored on the digital recorder, or it can be checked via using the CRT display or CRT monitor. So during transmission, the pulse which is generated by the pulse generator, it is of a specific wavelength and duration, and it is defined by the pulse length which is measured in microsecond. And as the wavelength of the microwave radiation are much longer, the microwave energy is measured in the centimeter, and we can see the electromagnetic radiation in the microwave region are classified into different bands. So these unusual names associated with the radar wavelength are the artifact of the secret work on the radar remote sensing in World War II, when it was compulsory to use an alphabetic descriptor for the signal instead of the actual wavelength or frequency. The shortest radar wavelength are designated K bands, but these are partially absorbed by the water vapor, and due to this reason the cloud penetration is limited. But this K band is mainly used in the ground based weather radar which are used to track the cloud cover and precipitation. But in the orbital and suborbital platform, X band is the shortest wavelength used, and some radar systems use more than one frequency, and they are referred as multiple frequency radars. So here we have different bands, their frequency range, their wavelength range, and their typical application. So we can see Ka, K, and Ku, these are having the shortest wavelength, but they are rarely used in the side looking airborne radar. So, in case of suborbital and orbital platform, X band is the shortest wavelength used in the radio detection and ranging. There are additional parameters that we must know, like azimuth direction, radar range or look direction, depression angle, look angle, incident angle, and polarization. So we will understand each of these parameters considering an airborne radar system. This is airborne radar system, means the active microwave remote sensing system is placed on the aircraft, and the antenna is mounted beneath and parallel to the aircraft fuselage. Here we have the first point, azimuth direction. So, this is the flight direction, means the aircraft is traveling in a straight line in this direction. So, the direction in which the aircraft is flying is referred as the azimuth direction on the ground. So, the flight direction is referred as the azimuth direction. Now, the pulse of microwave radiation generated at this system illuminate the strips of terrain at either side of the flight direction. It can be on the left side or it can be on the right side. So this direction is at right angle to the aircraft's direction of travel. So it can be either towards left or it can be towards right. So this is referred as the range or look direction. Means if the aircraft is traveling in this direction, this will be the azimuth direction, and the either side, either it is left or right side, it will be range or look direction. So this range or look direction for any radar image is the direction of the radar illumination, and it is at right angle to the direction of the aircraft. Suppose if this is the azimuth direction, so the look direction will always be at the right angle to the direction of the aircraft. In side looking airborne radar, system illuminate the terrain on one side of the aircraft but not beneath it. So this can be either on the left side or on the right side. And the pulse of energy sent out in the range direction illuminate only a certain part of the terrain. So if we consider this area on the ground, as we can see here, this is the radar beam which is illuminating this much portion on the ground. So the terrain which is illuminated nearest to the aircraft in the line of sight, it is referred as the near range. And the farthest point of the terrain which is illuminated by the pulse of energy, it is referred as the far range. And the image swath or swath width, it refers to the strip of the Earth's surface from which data are collected by the side-looking airborne radar. Look direction has a significant impact on the feature interpretation because the extent to which linear features are enhanced or suppressed on the imagery, it depends on their orientation relative to given look direction of the radar illumination. Objects that have their position in a direction perpendicular to the range or look direction, they are enhanced much more than those objects in the terrain that lie parallel to the look direction. Next is depression angle. This is angle between a horizontal plane extending out from the aircraft fuselage and the electromagnetic pulse of energy from the antenna along the radar line of sight to a specific point on the ground. So यहाँ पे this is the radar beam which is illuminating this much portion on the ground. So this is referred as the radar line of sight. So the angle between the horizontal plane along the range or look direction and the radar line of sight is referred as the depression angle. Now, if it is with respect to the far range line of sight, it will be far range depression angle. And if it is with respect to the near range line of sight, so it will be the near range depression angle. Let us have more clear visualization of the same. Consider an aircraft flying from the screen towards you, and it is flying at this much altitude above the ground. And the system placed on this aircraft is illuminating the left side of its terrain. So, this will be the range or look direction. So the radar beam which is transmitted from this system towards the terrain is falling in this much area. So the part of the terrain which is near to the aircraft is near range and this is far range. So the angle between this range or look direction and line of sight is referred as the depression angle. And if it is with respect to the far range line of sight, it will be far range depression angle. And if it is with respect to the near range line of sight, it will be near range depression angle. And the average depression angle of a radar image is computed by selecting a point midway between the near and the far range in the image strip. Next is look angle. This is the angle between the vertical from the antenna to the ground and radar line of sight. So here we have the look angle. So let us have the same visualization again. Means the aircraft is flying from the screen towards us. This is the vertical line from the antenna to the ground. This will be range or look direction. This is the pulse of beam illuminating this much part of the terrain. Now the angle between the vertical from the antenna to the ground and radar line of sight, it is referred as the look angle. Now again, if it is with respect to the near range line of sight, it will be near range look angle, and if it is with respect to the far range line of sight, it will be far range look angle. So here we have the mention of near and far range look angles. Next we have the incident angle. So when this pulse of microwave energy strikes on the terrain, so angle between the radar pulse of energy and the line perpendicular to the earth surface where it makes contact. So this is referred as the incident angle. In case of flat terrain, the incident angle is assumed to be complement of the depression angle. But if the terrain is slopy, there is no relationship between the incident and the depression angle. Next is polarization of the radar signal. Unpolarized energy, it vibrates in all possible direction perpendicular to the direction of travel. But the radar antennas, they send and receive the polarized energy. Here z-axis is showing us the radar signal propagation, and the red one is showing horizontally polarized signal, and the blue one is showing the vertically polarized signal, and the animation of both can be seen here. In radio detection and ranging, the pulse of energy is filtered so that its electrical wave vibrations are only in a single plane that is perpendicular to the direction of travel, and the pulse of electromagnetic energy sent out by the antenna, it may be vertically or horizontally polarized. Many radars are designed to transmit the microwave radiation that is either horizontally polarized or vertically polarized. So, when this transmitted wave of polarized signal interacts the terrain, it generates a backscattered wave with variety of polarization. So, in the radar, it is the analysis of these transmitted and received polarized combination that constitute the science of radar polarimetry. Different polarization for transmission or reception of the signal can be synthesized by using the horizontally or vertically polarized component. Thus, the systems that can transmit and receive both of these horizontally or vertically polarized signal are commonly used. There are four combination of polarization based on the transmission or reception of the signal. First is HH. Here system transmit as well as receive horizontally polarized signal. Second is VV. Here system transmit and receive vertically polarized signal. Next is HV. System transmit horizontally polarized signal but receive vertically polarized signal. And next is VH. Here system transmit vertically polarized signal but receive horizontally polarized signal. So the first two polarization combinations are referred as co or like polarized because the transmit and the receive polarizations are the same, while these two, that is HV and VH, are referred as cross polarized because the transmit and receive polarizations are perpendicular to one another. Radar system can have different levels of the polarization complexity. It can be single polarized, means it can have either HH or VV or HV or VH, or it can be dual polarized, means it is sensitive for two combination, HH and HV, or it can be VV and VH, or it can be HH and VV. And more advanced radar system can receive the signal for all type of polarizations. So this type of system is referred as the quadrature polarized radar or polarimetric radar because it uses all four polarizations and measures the phase difference between the channels as well as their magnitude. Here we have the difference between conventional radar and dual polarization radar. Conventional radar term is used for the radar system which are single polarized, and dual polarization radar is used for the radar system which are capable of dual polarization. Here benefit of dual polarization radar is shown over conventional radar in ground based radar system. In this conventional radar, HH polarization is used, and this is able to give us horizontal dimension of the snow, hail and rain. But in dual polarization radar, the system can measure the horizontal as well as vertical dimension, and it is able to detect the size of the snow, hail and rain. Some dual polarized radar also measure the phase difference between channel, and it is important in the polarimetric information extraction. If we have data from different polarization, a color overlay can be generated. For example, the red one is representing the HH polarization, means the system transmit horizontal waves as well as receive horizontal waves. The green one is representing HV polarization, means the system transmit horizontal waves and receives the vertical waves. And the blue one is representing the VV polarization, means the system transmit and receive both vertical waves. So when we have data from different polarization, three polarization color overlay can be generated for the better understanding of the terrain. So this was all for the part 1, the basics of microwave remote sensing. We will continue for the remaining topics in the next video. These are the references. You can refer to the book Remote Sensing of the Environment by Jensen, and some of the content have also been taken from these two websites. We will meet soon in the next video. Thank you and best wishes.